In this video, we're going to use a multi-layer perceptron, which is a type of neural network, to classify an incoming sound as either a trombone or an oboe. Neural networks can be used for a lot of different things. Classification is one of them. And when we do classification, we are predicting or identifying or categorizing or classifying which category an input belongs to. And in this case, as I said, our categories are going to be trombone tones and oboe multiphonics. One reason why we might want to do this is if we have a live performance, maybe involves improvisation, and we want our computer or machine to listen to the incoming performers, in this case, maybe a trombonist and an oboe player, and identify which one is playing at a given time. So the way that we're going to do this is we're going to get a collection or a corpus of trombone sounds and oboe sounds. Here we're just going to use sound files of different recordings of trombone and oboe. And we're going to first take all of the trombone sounds and do an audio analysis on them. For example, one could do analysis like pitch, the brightness of the spectrum, the noisiness of the spectrum, these types of audio analyses. And we're going to send those to the neural network as the input. And at the same time that we're sending that input to the neural network, we're going to also be telling the neural network with a label which instrument these analyses are from. So we're going to be sending the analyses in as input and saying, this analysis that I'm showing you right now, this is an example of a trombone. And then we're going to do the same thing with the oboe samples. We're going to use the same audio analysis, send those analyses to the neural network, and when we send it those analyses, we're going to say, this example that I'm sending you right now, this is an example of an oboe. And then once it has all of these examples, it has all of the oboe examples that are labeled oboe and all of the trombone examples that are labeled trombone, then the neural network is going to sort of make a guess on each one of these examples that we've shown it, and then check and see if it got the answer right. Or if it got the answer wrong. And if it got the answer wrong, then it's going to make a slight adjustment so that next time it sees that example, it can be a little bit more accurate. And this is how training works. And after making these guesses and slight corrections thousands of times, it'll be a lot better at making those predictions accurately so that then we can show it examples that it has perhaps never seen before by taking audio input, doing the same analysis, and sending it to the neural network. And then the predictions that it makes, the labels that it guesses as the output, will be based on the examples that we showed it before. So it'll make the prediction to say that this new example that you're showing me is most like the oboe examples that you showed me before, or the trombone, or whatever our labels or categories are. And here's the SuperCollider file that we'll start from. And when I'm completed with this, I will put a link in the description to the completed file that you can download. So what I have here, I'm loading two buffers. One is a recording of some trombone tones, and one is a recording of some oboe multiphonics. These sound files are downloaded when you download the FluCoMa package, and that's why this set of objects here is looking at where the MLP classifier is, what file it is in, and then from that path navigating to where it can find these files also inside of the FluCoMa package. So if we just listen to those, they are both mono files, so they're just coming out of the left speaker right now. And here's the oboe sound. Great. So the first thing I'm going to do is I'm actually going to take this sound file and I'm going to divide each of them into two sections. I want to use some of the trombone tones to train my neural network with, and keep some of the trombone tones for testing the neural network with afterwards to see how it's performing on those examples that it's never seen before. And I'll do the same with the oboe file. And what I've done is I've already looked in these sound files and identified that this is the number of frames that I want to use for the training set, and then the rest of the sound file I will use for the testing set. So I'm going to load these buffers again differently. And I would call this one trombone train, and I want to start at frame 0, but then only use this number of frames for my training set. And here frames means samples, right? So the actual audio samples. And then I'll do the same for the oboe. Start frame 0, number of frames, this many. And then I'll do a similar thing, and I'll create a trombone test and oboe test, which will be the section of the sound file that we'll use to test the neural network after we've trained it. And for this one, I'm going to start at this frame, and then the number of frames should be -1, which means just go to the end of the file. And I'll just double check that these are correct by using the fluid waveform object, and it'll let me load in these buffers and just look at them. So if I look at the full trombone here, I have 1, 2, 3, 4, 5, 6, 7, 8 trombone tones in the full file. And then if I look at just the trombone train buffer, I now have 1, 2, 3, 4, 5 tones in the whole file. So the remaining 3 will be in my trombone test buffer. And there we see the last 3. And we'll do that with the oboe as well. Here our oboe has 1, 2, 3, 4, 5, 6, 7, 8 oboe multiphonics. And the oboe train buffer has 1, 2, 3, 4, 5, 6. So hopefully the oboe test buffer will have the remaining 2. Great. So now we have our testing set and our training set split up so that we can have a certain set of sound files to just train the neural network with, and then another set of sound files to test it on after it's done training. And this is important to do because this is going to imitate a sort of real world scenario in which if we have an oboe player and a trombone player on stage and we want this neural network to classify which instrument it is hearing, the sounds that they're making on stage, of course, this neural network will never have heard before. And so we want to make sure that the neural network is able to perform well to accurately make predictions on sounds that are not in its training set. So the first thing we're going to do, I'm going to make a function. I'm going to call it real-time analysis. And that function, I'm going to pass it an argument buff, which will be which buffer, whether it's trombone train, trombone test, oboe test, that we want to do the analysis on. So once I pass that buffer in, I'm going to make a synth. So let's just test that and make sure it's working. So I'll make this function. Then down here, I'll say real-time analysis. We'll pass in the trombone train buffer. And now we hear it playing there. So what we really want to do is inside this real-time analysis function, and in the synth that is playing, we want to do an audio analysis. The type of analysis we're going to use is called MFCCs. And MFCC stands for Mel Frequency Cepstral Coefficient. In this video, I'm not going to get into what this analysis does or how it works, but it is a type of audio analysis that is often used for timbral description or timbral classification, such as what we're doing here. So it'll be a good analysis for us to use. I'll make a variable called MFCCs, and I will get this analysis from the Fluid MFCC object. Our input will be the signal we want to analyze, and we'll use the default number of coefficients here, 13, because I think it will work very well for us. The next argument I'll put in is start coef. The default is 0, but I'm going to put the value here 1. If we use the default 0, what it will do is it will start at the 0th, because we always start counting from 0 in these cases. It would start at the 0th coefficient and give me the next 13, which would be 0 through 12. By specifying start coef 1, it's going to hop over that 0th coefficient and start at coefficient 1 and give me the next 13, so 1 through 13. And the reason we're hopping over that 0th coefficient in this case is because the 0th coefficient represents the overall energy in the spectrum, which is related to how we perceive loudness. And we actually don't want our neural network to learn to distinguish between oboes and trombones based on how loud the signal is. We want the neural network to distinguish between these instruments based on the timbre. And so we're actually going to remove that 0th coefficient and the loudness information that it contains so that the neural network does not try to learn based on that loudness. So let's just see what this is giving us here. I'll put a poll here. We'll recreate that function and then we'll listen to it. But you can see what's coming out of our Fluid MFCC analysis here is 40 values, of which only the first 13 actually have information in them and the rest are just zeros. And this is because there's one more argument that we should give our Fluid MFCC analysis That is the last one here on the right. You can see max num coefs. And we're going to specify that max num coefs should be 13 because we're actually only ever going to want to use those first 13 coefficients. What we could do if we left it at 40 is we could modulate this parameter in real time, the number of coefficients that we want it to return to us, and specify that it should give us more than 13 coefficients. We could ask for up to the maximum that we specify here, the default being 40, but here we're just going to tell it we'll only ever need the 13. Now, since I'm using this number 13 in more than one place, I'm actually going to make a variable out of it. So let me recreate that function and then listen to it again. And now we can see that the analysis is in fact only giving us these 13 values. Now I'll point out here that this is showing us indices 0 through 12 because those are the indices in the array that it is returning. However, this isn't the 0th coefficient from the MFCC analysis. This, because we specified start coef1, it is actually starting at that not 0th but first coefficient. Now that we have these audio analyses, we're going to want to add them to a data set. But before we can add them to a data set, we first need to write them into a buffer. And in order to do that, we're going to use an UGen on the server here called FluidKR2Buff. And what KR2Buff will do is take this stream of control rate values coming out of our analysis and write them into a buffer. So I will say our KR stream is going to be MFCCs, and the buffer, we'll make a buffer, we'll call it MFCC buff. And for the number of frames in this buffer, because we know we're going to be writing these 13 MFCC values into the buffer, we can just allocate this buffer to have that many frames. So we're going to say the number of frames should be 13. Now I'll recreate this function, play some sound, and then I'll go and look at what's in that buffer. So I'll say MFCC buff.plot. And we can see that there's some values in that buffer that are the MFCC values being written into it by our FluidKR2Buff object. I'll double check it by just playing some oboe sounds as well. We can see that there are also some MFCC values in the buffer here, and they look a little different, which is good because hopefully that will help the neural network be able to use these values, this analysis, to distinguish between the two instruments. So as this synth plays, Fluid MFCC is continuously outputting these MFCC analyses, and they are continuously being written into this buffer. So now whenever we're hearing this trombone sound or oboe sound being played by this real-time analysis function, we can be sure that in that buffer MFCC buff are MFCC analyses that are coming from the analysis of the trombone or the oboe. We can then add them to a data set. So I'm going to make a data set to add them to. And I'll make a function down here called addPoint. Each time we add a point to the data set, we're going to have to provide it with a unique identifier. So I'm going to make a variable here called ID, and we'll make that identifier a string that starts with the word example dash. I'll put a percent sign in here that will replace using format. And what we will replace the percent sign with is some integer that will make sure that each one of these strings, example dash, will be unique. In order to do that, I'll make a counter. And then after we use that counter, I better increment that counter so that it will be different the next time we want to use it. To add a point to the data set with this identifier, we will tell the data set timbre data to add point. And it takes two arguments. The first one is the identifier. The second one is the buffer that the data set should go check and see what values are currently in there, and then take those values out and add them to the data set. And that buffer where we're writing our timbre analysis, our MFCCs, is called MFCC buff. Each time we add a data point to our data set, we want to have some way of knowing which instrument that data has come from. And we're going to do that by adding labels to a label set. So I'll go up here and I'll say labels equals fluid label set. And we will add these labels similar to how we added data points by saying labels.addLabel. Now this also is going to take two arguments, the first of which is going to be an identifier, and we'll use the same identifier so that the label we add to the label set can be associated with the data point that we've just added to the data set. Here, the label that we're going to add, I'm just going to put a variable called label so that what we can do when we add point is pass in an argument called label, which will be a string, either trombone or oboe in this case, to specify which label we should add to the label set. So let me create all of those functions here and then play some sound and try to add some points. So I'll say add point, and then the argument I will pass is trombone because we're going to play trombone sounds. And let me see what happens here. I'm going to add points by just executing this line of code over and over. Each time I execute it, it'll add a point. And let's just go see what's in the data set. So I can do that by telling the data set timbre data print. And we can see that it has 20 rows. So that means I've added 20 data points. Those range in identifier from example 0 to example 19. And each one of these data points has 13 columns, meaning it has 13 values, which is good because that's how many MFCCs our analysis is providing and how many we're writing into that buffer. Let's also check the label set. I'll say labels.print. Label set also has 20 rows, meaning I've added 20 labels to it. They all are trombone. And they also range from example 0 to example 19, which is good because that means that the labels in my label set are paired with the data points in my data set with that unique identifier. In just a moment, I'll start adding a lot of points to our data set and label set so that we can use all of that information to train the neural network. Right now, I'm just going to clear both of these. I'll say timbre data.clear. And if we print it, we can see that it is in fact empty. And I will also say labels.clear. And if we print it, we can see that that is also empty. Okay, so I will do my real-time analysis, then I'll add a bunch of trombone points, and then I will do the real-time analysis on the oboe training set, and I will add a bunch of trombone points. Now you'll notice that I'm going to avoid adding points during these little gaps of silence, because during those little gaps of silence, the audio that's being analyzed isn't an example of a trombone. So the MFCCs that are coming out of the analysis are not going to represent a trombone, they're going to represent that silence, and I don't want to add them to the data set and to the label set with the word trombone. Now let's do some oboe points. Oh, I better call this oboe. Again, I'm taking care to not add points during the gaps of silence, since I don't want the neural network to think that those analyses should be called oboe. I'll leave these test buffers down here a little bit lower. And now that we have all of our training data, we have all of the MFCC analyses, which with a shared identifier are paired with labels in our label set, we can train the neural network. So here's the neural network we're going to use. I'll call it NN for neural network. We'll use the Fluid MLP classifier. Now I'm going to put some arguments in here that I think will work well for us, but in this video, I'm not going to go into what they all represent. There will be a link in the description where you can learn more about all of these arguments and how you might adjust them to get a better result. So I'll initialize the neural network. And then in order to do the training, we will just call .fit. And fit here is synonymous with train. It's like we're fitting a curve to data points. .fit takes two arguments. The first is what data set has the data it should use as input to the neural network, and that is where we've been putting our MFCC analyses. That data set is called timbre data. And the second one is the label set that has the labels with corresponding identifiers to know which label it should predict for all of the input data points. And that is the label set we've been using called labels. Now we'll give it a third argument here of an action function that will execute when it has completed training. And it will pass to that function an argument that is the loss or the error. And this value essentially represents how inaccurate or how wrong the neural network still is at performing the task that we've asked it to. So lower is generally better here. It means it will be less inaccurate or more accurate. I'll post the loss here and we'll see what comes out. It returns a value, so we know that it has completed its training, and it gives us a loss of 0.0017. Now, there's no objective way of knowing that if the loss value is lower than a certain threshold that the neural network will work for you or won't. With the neural network training, the best thing to do is always to just test it, hopefully on data that it has never seen before, which is why we created our oboe test and trombone test buffers that we didn't train it on, so we can see how the neural network performs on these timbres. In order to test it on these timbres, what we'll do is we'll say nn.predict point. And predict point is going to take one argument here, and that is which buffer it should use to get the data out of to use as input to the neural network. Now, we're already writing our MFCC analyses into a buffer. That is our MFCC buff. So we're going to put that buffer in here. And then this action will actually execute once it has completed making its prediction, and it will pass to it what it thinks the prediction is. So that'll be the label that it predicts for this input. Now it will use the same real-time analysis function to play back our trombone test buffer and our oboe test buffer so that these sound files will be analyzed. Those analyses will be written into our buffer MFCC buff, and then I will click the predict point function so that the neural network will go look at that buffer, use it as input, and make a prediction. And remember, these examples the neural network was not trained on, so we'll know whether it is performing well. So it seems to think that all of this is a trombone, which is great. Let's see how it does on the oboe file. It thinks all this is an oboe, which is great because it is. So now we have our neural networks successfully predicting or classifying, distinguishing between trombone and oboe. There's one more way that we might want to do this classification, and that is to keep everything happening on the server. So I'm just going to comment out this stuff here, and we'll make a function called server predictions. And we will pass to server predictions which buffer we want it to play and analyze. So I'll make an argument buff. And then we're going to do something very similar to what we did with the real-time analysis synth. So I'm just going to copy and paste it here so that we can have this in our server predictions function. So it'll take this buffer, it'll play it back, it'll do the MFCC analysis on it, and write it into our buffer MFCC buff. Now what we're going to do is we're actually going to put the neural network right here and say nn.kr. And this is our MLP classifier that we have trained. And we're going to give it a few arguments here. The first one is a trigger that should tell it when to make predictions. So it's not going to be constantly making predictions. We actually have to trigger it to tell it when to make a prediction. I'll just say here impulse to tell it to make a prediction 30 times a second. So updating quite frequently. The second argument is going to be which buffer, again, it should use as input to the neural network. We're already writing our MFCC analyses into our MFCC buff. So I will put that here, MFCC buff. And lastly, it's going to want a output buffer into which it will write the prediction that it makes. Now, because on the server, we can't really output a string, whether it be trombone or oboe, it's actually going to output an integer. And that integer is going to represent the position of the label in the order in which the labels were introduced into the label set. So, because we first added a bunch of trombone points, if this integer it returns is 0, that's going to mean trombone, because we always start counting from 0 in these cases. And if it returns a 1, that's going to mean oboe, because we added the oboe examples after the trombone examples. Now, the buffer that we're going to write that integer into, we haven't made yet, so we'll make that, but we'll call it predictions. And this buffer will just be one frame, because we're just going to write one value into it. Now, in order to see what is in this predictions buffer, we have to read out of that buffer, and we'll use that with an object fluid buff2kr. And it does just what it sounds like. It will read those values out of a buffer and return it as a control rate value. So that buffer will be our predictions buff. And what I actually want to do is send this back to the language, and we'll catch it in an OSC def. So I will use a send reply.kr. We're using this impulse here, so maybe I'll make a new variable called trig. And then our send reply will say that the command is prediction, and the values will be whatever is in that buffer. Now I also will make an OSC func here every time we're starting this synth inside of our server predictions function. We'll want to say OSC def. We'll call it predictions, and we'll tell it that it should listen for prediction. And then we'll just post the message here, and we'll just post index 3, since those first few indices are just information about the message. So we can see if we can make this function. Great. We'll call the function down here, server predictions, and maybe we'll pass it our trombone test buffer and see what happens. So we can see it's predicting all of these zeros, and that's good because that's what we're hearing right now is a trombone. We can see that there's a couple errors in here where it's actually predicted oboe. We'll look at a way to fix that in a moment, but first let's also test it on our oboe test file. Good. A lot of ones here. It definitely thinks that this is an oboe, which is good because it is. So if we just watch that one more time, we'll see that there's a couple that it gets wrong sort of in the middle of the oboe multiphonic here. See a couple zeros that flip in right here, right there. Here's one. So it's getting a few of these predictions wrong. It could be that we need to add more data. We could train the neural network more. There are some things we could try to do to try to have it be more accurate through all of those moments. But there is one thing that I noticed that I think we can fix rather easily, and that is that if you watch the little silent gaps here, so we're hearing the oboe timbre, and then during this gap of silence, it reports back a lot of zeros right in a row here. It gets very confused during the silence. And that's because the neural network doesn't have any ideas about silence. We've only told it about trombones and oboes, so it will only ever be able to report back one of those two predictions. There are a few ways we could approach this, but one thing we could do is we could actually just tell the neural network to not make predictions during silence. In order to do that, we will make a variable called loudness, and we'll get that value from our fluid loudness analysis. We'll pass in the signal that we want it to analyze, and fluid loudness returns two values. The first one is a loudness descriptor in decibels, and the second one is a true peak descriptor, also in decibels. We just want to use the loudness one, so I will just ask for the 0th index of those two channels here. And then I'm going to make another variable called thresh. We'll make our threshold for loudness and silence be -40 decibels. And lastly, we'll make another variable called isPredicting. And this will just be a Boolean variable, either 1 or 0, to indicate to the neural network whether or not it should make predictions. And this will just say if the loudness is greater than or equal to thresh, then isPredicting should be 1, and otherwise it will be 0. So now what we can do is we can take this isPredicting variable and multiply it by our trigger here. So if predicting is 0, these triggers will just be 0. They'll all be multiplied by 0, so the neural network won't do any predicting. And if isPredicting is 1, then the triggers will be multiplied by 1, so they will be triggering the neural network and it will be predicting. We can also do it right here so that we'll only send these prediction values out of this fluid buff to KR if we want it to be making predictions. We could also send another message, 1 minus isPredicting, which will flip our isPredicting Boolean so that when it is predicting, this will be a 0, and we won't send triggers to this send reply. And when this is a 1, 1 minus 1 will equal 0, so we won't send triggers to this send reply. We'll still send to our prediction OSCDef, but instead of sending the value out of the buffer, we will send a -1. -1 meaning it is not a 0 representing trombone, it is not a 1 representing oboe, it is a -1 suggesting that it is silence. There's our function, and now if we'll play the trombone test, we see that it's all -1s before the trombone starts playing, and then once it starts playing, we're getting 0s. And hopefully we'll get that again during the little gap of silence here. There's -1s during the silence, and then 0s during the trombone. And then -1s right at the end there. Oh, there's some more trombone. And then -1s at the end for the silence at the end of the file. Let's try it with the oboe test buffer. Great, so we had some -1s, then we have a lot of 1s here for the oboe. And then during the silent bits, we get -1s and the 1s again for the oboe sound. Now there's still a couple spots where the neural network is getting confused and returning some 0s. So again, we could do some things where we might want to add some more data points to the data set and label set and retrain on those, or train the neural network more to try to decrease the loss value to get it to perform even better. Those all would be good strategies to try to make it more and more accurate. So here we have our neural network that we've trained using examples from oboe and trombone sound files. We've made predictions using our predict point message to the neural network, and we've made predictions on the server using the .kr method for our MLP classifier.